we said some time ago that row rank is the same as column rank for a general matrix, so m by n matrix, not an n by n matrix. And we saw that the row reduction, the process did not change the row space, so it did not change the row rank. And row reduction of a general matrix will give you as many rows as the rank of the matrix, and there will be an identity matrix hiding there. So I'm talking about Gauss-Jordan elimination. An identity matrix shuffled in with columns corresponding to free variables. And suppose I call this guy by a name R1. I know that the row space of R1 and A will be the same. So the row rank of R1 and A will be the same. The dimension of the row space, that will be the same because the row spaces are the same for these two matrices. Now, that's because the row operations do not change the row space. And if I want to think about the column rank, I can apply, starting from R1, I can apply column operations on that without changing the column space of that matrix R1. So if I do that, I will eventually get a bunch of 0 columns, because just like we got 0 rows by doing row operations, we'll get 0 columns, and I'll get an identity matrix by itself. That is a different matrix R2. So the column rank of these two matrices will be the same. Column rank of R2 will be the same as the column rank of R1, and the row rank of R2 will be the same as the row rank of A. So this is because the column operations do not change the column space. So the column rank of R1, in other words, you can see that the row rank of and column rank of this particular matrix here is just R, because everything else is 0. We reach there without changing the row space and the column space. Row rank is equal to column rank. But we know this in many different ways. We know that row rank is the same as the number of linearly independent rows, which is the same as the number of pivots. Column rank is the number of pivots looking at from the column side, and there is only one set of pivots. We proved it in many different ways. This is another proof that I saw somewhere, and I thought I would share this also with you. Another thing I want to say, it is probably a bit beside the point and a bit more involved than the other one. Rank of A is the same as rank of A transpose A is the same as rank of A transpose. So that is done by looking at the null space of these guys and comparing it to the null space of A, and then using the rank nullity theorem. And I would ask you to go through this proof and understand it. But what I want to highlight is this fact. Rank of A is the same as rank of A transpose, is the same as rank of A transpose, and most importantly is the rank of the gamma matrix A transpose A. That we have to remember. So that brings us to the gamma matrix. For a full column rank tall matrix, n is the number of columns, so all of them are linearly independent, so the rank is n. We looked at it, and that was the basis of linear regression, least squares, etc. A transpose A is a small matrix. M is much bigger than n, so many more rows than columns. Take A transpose A, that becomes a small matrix, and that is full rank because the rank of that guy is the same as the rank of A. And now A transpose A is n by n, so every column has a pivot, every row has a pivot. So it's a very nice matrix, and we saw that it was positive definite too. So it's like the king of matrices here. So it's got many applications in machine learning. In statistics, for instance, the covariance matrix after doing the zero centering, similarity of matrices.